has horizontal and slant. Not possible. It can have vertical and horizontal, yes. It can have vertical and slant, yes. But it cannot have all three. It can have either horizontal or slant. Okay. So there are three major types, of rational functions. I would say three major types. There are others, of course, but the three major types are degree n over degree n. The horizontal asymptote is y equals leading coefficient, as you know from pre-calculus, over the leading coefficient. Let me make sure that this is LEAD. Sort of. And the second possibility, degree n here and degree less than n here. And the third possibility is degree n plus 1. And just to make sure you don't think that there are only three types, other. We will only look at 1, 2, and 3. The other require a lot of work with the calculator. We can choose other situations. This one has a horizontal asymptote that's the leading coefficient over the leading coefficient. This one has the horizontal asymptote only and always 0. And this one has no horizontal asymptote, but slant, also called oblique asymptote. Okay, so I'm going to ask you to choose a problem like this because they are so similar, and a problem like that, or I will. So I'm looking for rational functions. Here we are. Especially, definitely we need one with a slant asymptote, because I want to illustrate that. But before we do directly the slant asymptote, we're going to, let's look at a rational function. I don't remember doing any. Please correct me, have we done any? Even if we had, it's okay. We need more practice for rational anyway. Okay, so first of all, I noticed that this function, so the whole thing is to graph this function and show everything that you can possibly determine about this function, from the derivatives, just everything. Fill out the table. I see that the numerator is x plus 2, x minus 2 in the factor form, and the denominator is x times x minus 2. Do not rush to simplify. You cannot do that just yet. There will be a mistake. Let's get our table started. And in the table, of course, I have x, the variable in the problem. I have f prime. I have f of x. And I have the second derivative. Okay. Can anyone give us the domain of this function? Anyone? Can anyone give the domain of this function? Anyone?
All real numbers except 2 and 0.
Thank you very much. Good. Then I can simplify, And the simplified form is x plus 2 divided by x. Because the factor of x minus 2 is going away, I know that x equals 2 is a hole in the graph. Because the factor of x does not go away, I know that x equals 0 is a vertical asymptote. In the function, I cannot plug in 0, but I can find y equals 0, means x plus 2 over x is 0. A fraction is 0 only when the numerator is 0. So I get x equals negative 2. So negative 2 is the x-intercept. So negative 2 comma 0. Since I keep putting this page away, I'm going to copy my function here so I can indeed put it away. Okay, and my next point is to find these. After this is done, then I will go to the first derivative, not before. So the limit, this is a very interesting function because you know me, I'm all about simplifying and factoring. If you separate this into two fractions, you have 1 plus 2 over x. And this is so helpful, if you notice that, for all the limits that we need to determine. So then I have the limit as x approaches negative infinity from 1 plus 2 over x. It's very clear this approaches 0, so the limit is 1. And it will be the same for x approaches infinity. It doesn't matter, it will still be 1, which means y equals 1 is a horizontal asymptote. 1 here, 1 here, make myself a note, y equals 1 horizontal asymptote so I don't forget. Every time I discover anything about the function, I put it in the table so I don't forget it when I graph it. Okay, the limits left and right of 0. So I have limit as x approaches 0 from the left of 1 plus 2 over x. Actually, I prefer x plus 2 this time over x. And the other limit as x approaches 0 from the right from x plus 2 over x. Okay, I know that the numerator is positive and the denominator is 0. And we talked about this a long time ago. This situation has positive infinity, negative infinity, or DNE. So 0 from the left, that would be negative 0.1. The top is positive, but the denominator is negative. So the answer is negative infinity, and I put it in my table. The same thing here is positive, positive. So this is positive infinity, and I put it in my table right away so I don't forget. Now I have to determine the limits left and right of 2. So limit as x approaches 2 from the left, and limit as x approaches 2 from the right from x plus 2 over x. X plus 2 over x. Oops, I meant to put the comma here. Okay, so 2 at the top, it's 4. Denominator is 2, so this is 2. And this is 2, so this is 2 and 2. So I know the whole will be 2 comma 2. And this is done. Done. There is nothing else I can find about the function from the function itself. Okay, now next, I have to, and I love this form, absolutely, when I differentiate, not that, this. So now I have to find the first derivative, and I have negative 2 over x squared, which is nice, because it's always negative, which indicates because this is always positive. If this is always positive with minus in front, will be negative, which means the function is decreasing forever, according to the relationship between the sign of the first derivative and the function. Okay. Now the moment of truth. That's when I say, uh-oh. If that's the case, I hope it's not the case, but who knows? From 1 to 0, yes. From 0 to negative infinity, indeed. From infinity to 2, yes. From 2 to 1, yes. Now I'm ready for the second derivative. And of course, I'm going to differentiate, but not this. I'm going to differentiate this. And when I differentiate, I get 4 times x to negative 3, which is this, which is never 0. No inflection points. But I need to study the sign. So when I plug in a number to the left-hand side of 0, this whole thing is negative. When I plug in a number to the right-hand side of 0, whole thing is positive. It's not symmetric, and I have to mention that. Not symmetric. F of negative x does not equal f of x, and it does not equal negative f of x. If this were true, the function would have been even. If this were true, the function would have been odd. None of the above. And this is it. Now I'm ready to graph. When I graph a function with asymptotes, I have to graph the asymptotes first. They're not part of the graph. So this has a horizontal asymptote y equals 1 and has a vertical asymptote at 0. This is an overkill because the y-axis is there anyway. I have to plot this point, which is 2, 2, which is a hole, and the negative 2, 0, which is the x-intercept, the only x-intercept. I read my graph now, my table now. From approaching 1, horizontal asymptote, crossing at negative 2, 0, opening down and decreasing to negative infinity. No problem. On the other side of the vertical asymptote, coming from positive infinity, decreasing, opening up, decreasing, opening up, going through the hole, still opening up, decreasing towards the horizontal asymptote. No problem. So this is the function f of x equals x squared minus 4, I think it was, x squared minus 2x. The original function. Yes, that was it. Yes, if you want to graph it with a graphing calculator to check your work, go to y equals, clear whatever you have, but you have to add the horizontal asymptote as an additional function as y equals 1. Do not forget to put parentheses around the top and parentheses around the denominator, because otherwise you will graph something else. And divided by, in parentheses, x squared minus 2x. You will not be able, the calculator is not as sensitive. If you use the zoom, if you use the standard viewing window, you're not going to see that open point. Let's use standard just for a moment to see the graph. It's very clear, and the horizontal asymptote. If I'm asked to find the range of this function, can anyone give us the range of this function? Negative infinity. Yes.
Yeah, all real numbers except 1. Right. Oh, right. And 2.
Exactly. Oops, oops. Yep. Except 1 and 2. Except 1 and 2. Yep. Anything else here before we look at a function with rational function with slant asymptote? Okay, I'm going to choose 1. Feel free to choose yourselves if you would like. So remember, the slant asymptote must be a function with a higher degree in the, higher degree in the numerator by 1 unit higher in the numerator so that the division is a line. Sorry, please make the correction here. The degree of the numerator has to be by exactly 1 unit higher than the degree of the denominator, so that the division, the quotient, is a line. So when we divide degree 3 by degree 2, the quotient will be a line. And this is the slant asymptote, plus remainder over the divisor. So any degree like 3 and 2, 10 and 9, 5 and 4, will give us a quotient that is a line. That line, just that line, that piece will be the slant asymptote. If it has a remainder or not, it doesn't matter. So most probably we'll have a remainder. So remainder over the divisor. So that's the reason why this has degree 1, because the numerator is by 1 unit higher than the degree of the denominator. Otherwise, we will not get a line. So let's see how this works. And